Hi, so my name is Bill Buchanan, and I'm here with a true world leader and someone who has had a massive impact on the lives of virtually every person on the planet, Vint Cerf. Hi, Vint.
Well, good afternoon to you, and it's morning for me here in Washington, D.C.
Great. I'm in Edinburgh, and it's kind of later afternoon. So, and you'll be glad to know it's kind of wet here. So, it's,
Well, why am I not surprised to hear that? I was in London. I was in London last week, and it
uh,
was magnificent weather,
magnificent.
unusual for late September.
That's right. Yeah. So Vint is seen to be one of the founding fathers of the internet, and along with Robert Kahn, was awarded the AM Turing Prize, which is the Nobel Prize of Computer Science in 2004. Vint contributed to many areas in the creation of the internet, including writing many RFCs. RFC is request for comments, drafts, and in 1974 published the classic paper of a protocol for packet network intercommunications in the IEEE Transactions on Communications. This paper basically defined the building block of the internet, which was IP and TCP, and that would eventually be used to create the infrastructure that we now call the internet. The internet. Along with the AM Turing Prize, he received the National Medal of Technology from President Clinton. Please tell me if I get these presidents wrong. Uh, in
So far,
19,
you're correct.
yeah, 1997, the Presidential Medal of Freedom from President George W. Bush, and the Marconi Prize. Vint has received, I think, 20, at least 27 honorary degrees from universities around the world, including top universities such as Zurich, Yale University, and the University of St Andrews in Scotland. You'll be glad to know. In 2012, he was inducted into the Internet Hall of Fame, and in 2023, he received the IEEE Medal of Honour for co-creating the Internet. It's just a small thing like creating the Internet, and for sustained leadership in the creation of the Internet as a critical infrastructure. To say critical infrastructure is underselling the importance of the Internet. So, what were you like as a student at is it Van Hughes High School? Is that how you pronounce
It's
it?
actually called Van Nuys.
Van Nuys
Van Nuys.
High School. I did notice that and you and Steve Crocker and John Postel, we'll be talking about them a little bit later, also went to the same school. So, what was it about that school that created so many of the architects of the internet, or was it just something that just happened by mistake?
Well, I don't know that it was a mistake, but I think it was coincidental. This school, it was an interesting one because it was in the north of Los Angeles. It's in the San Fernando Valley, which was a residential community for a long time. Uh, Van Nuys High was located kind of in the center of the San Fernando Valley, and some of the other people who went to Van Nuys High included Marilyn Monroe, uh,
Wow.
Don Drysdale, a baseball player, Stacy Keach, another actor, Natalie Wood, uh,
Well,
Robert Redford. I mean, there's some amazing names that went to that high school. Now they were there before I got there, so I can't claim any. Except Stacy Keach was two classes behind mine, so I was at school just as he was finishing his senior year. Steve Crocker ended up there um, in almost by happenstance. His family had split up, and he was going to high school in Chicago, and his father lived in Van Nuys, and so eventually Steve ended up living with his father in Van Nuys, and we met in 1959, I believe. So we've been colleagues, friends ever since. I mean, he was my best man at my wedding, and I was his best man at his wedding. We've done business together. We still work together on a bunch of different projects. So Steve and I have a very, very close relationship that has gone on over 60 years now. John Postel, interestingly, was in the class after Steve's, and Steve was in a class after mine. And we didn't know John while we were all in the same high school together. We didn't actually meet him again until we all ended up at UCLA doing our graduate work. And all three of us were working in Leonard Kleinrock's laboratory, which was serving as the network measurement center for the ARPANET project, which was the predecessor to the internet. So Postel was one of the three of us working in that group, and as we'll discuss later, had a very central role to play in the evolution of the internet. So it's pure happenstance that the three of us happened to be at the same high school, and it's even more coincidental that we all ended up at UCLA, all working for Len Kleinrock. And as is true of much history, none of this was planned, and much of it was fortuitous. And of course, looking back over some 60 years, it was a hypergolic relationship. And for your listeners who don't know what hypergolic means, it means when you mix two things together, they explode.
Yeah. And you selected maths, computer programming, a very technical focus. Why did you go down that field?
Well, I didn't expect to, because back in those days, I was in high school from 1958 until 1961, grades 9, 10, 10, 11, and 12. And the computers were not readily available then. They were very expensive in the late 50s and early 60s. But by happenstance, Steve Crocker, a very, very bright mathematician, got permission while he was still in high school to get access to computers at UCLA, which were in, over the hill to the south of our Van Nuys High School. So in evenings and on weekends, we were able to get access to a very old machine called the Bendix G15, which was very new at the time. It was a numerical control computer using paper tape for programming and for punching out its results. And we got permission to use that computer. And so we were playing with it by writing programs that would generate transcendental functions so that we could, it's like 2 to the x equals x squared or something like that. Just because it was fun to make the machine do what we wanted it to do. So I got interested in this around 1960. And I'd been introduced to computing, but not with any hands-on experience, 2 years before that in 1958. Because my father had a good friend who worked for a company called Systems Development Corporation in Santa Monica. And they had a training center for what was called the SAGE system, which stood for Semi-Automated Ground Environment, which was a collection of computers that were interconnected and which were taking distant early warning radar signals from the northern part of Canada, bringing them back on 2400 baud lines to the SAGE computers in an attempt to detect Russian bombers coming over the pole. So this was during the Cold War, and there was a lot of concern that that could be a threat. Of course, they needed to make sure they distinguished between Canadian geese flying over the border and Russian bombers. I think the Canadian geese did more damage than the Russian bombers ever did. But this machine was made out of vacuum tubes, the sort of things that radios and television sets used to be made out of. And so it was so big that you literally had to walk into the computer to use it. The walls were covered with these vacuum tubes. So I was quite astonished and fascinated by what I was seeing in 1958. And when an opportunity came along to actually write programs in 1960, I took that opportunity. And then I went to Stanford as an undergraduate. And although I was in the mathematics program, I took every computer course I could take because Stanford had some very new Burroughs 5500 machines, very, very clever architecture. I mean, a tour de force of technology at the time. So I took every computer programming course I could. And when I finally graduated in 1965, I decided maybe I should find out whether a career in computing would make any sense. And the result was I went to work for IBM in Los Angeles. And I was, this 65 was the year after the introduction of the IBM 360, which was a
360.
huge transformation for IBM because all machines of all sizes were interoperable and compatible, had the same instruction set, unlike the many different models that IBM had made up until that time. So I got experience working at IBM with time sharing systems. I was responsible for, I was a systems engineer for a time sharing system called QuickTran. After a couple of years, I realized that I really needed to go back to school to learn how to design an operating system and, you know, what's a programming language and how do you design a compiler for it. There were so many things I didn't know. So I called my friend Steve Crocker, who at that point was in the graduate program at UCLA, and he introduced me to his thesis advisor, a man named Gerald Estrin, who eventually became the chairman of the computer science department. And I became Gerald Estrin's student and joined the university as a graduate student in 1967. So, my career path has been very dramatically affected by the presence of computing and the opportunity to write software.
Yeah. And obviously the System 360 was such an advancement at the time because, as you said, every different system had their own operating system, their own programming language. Obviously, IBM brought forward Fortran 57, as I
Yes,
remember,
yes,
which was the original one. And then you would maybe have BASIC and COBOL. COBOL was around then? Was that?
yes, COBOL was around because that was one of the earliest of the commercial programming languages. And if I
Mm.
remember right, Admiral Grace Hopper was one
Yeah.
of the authors of COBOL. And I remember I was a heavy user of Fortran uh, fairly early on because I wrote software for a company called Rocketdyne,
Mm.
which made the F1 engines for the Apollo uh,
Mm.
Saturn rocket, the first stage of the Saturn rocket. We had test facilities in Santa Susana Mountains north of the San Fernando Valley. Rocketdyne was in Canoga Park, which is in San Fernando. And I worked there around 1961 for 6 months, writing software to analyze the test data that we got from testing the rockets in a fixed jig, just to make sure the rocket would survive until it ran out of fuel, after which we didn't care anymore. Unlike Elon Musk, who likes to reuse the first stage, and
Yeah.
that's certainly a major advance.
Yeah. And I suppose this was the time before mini computers, because I remember mini computers came along with DEC, digital DC. So these were massive computers that had people with white coats, technicians to
Yeah,
look after them.
when I worked at IBM, I was actually, oh, there's a sad part of the story. When I joined IBM, the first thing they did was send me to systems engineering school, and they taught us how to assemble physical components to do computations. Uh, it was called programmable printing. That basically you read in cards in a card reader and you took the data off the card reader and you ran it through a bunch of physical modules, which you had physically wired together to do the computation, and then the output would go to the printer. They taught us how to do that in 1965 after the 360 had been released. So, I don't know why the hell they were showing me how to do that. But then I was supposed to go to Los Alamos to install a 36091, which was the top of the line, fastest supercomputer available. And of course, I'm pumped and excited. And 3 days before I'm supposed to go to Los Alamos, they say, no, we want you to stay in Los Angeles and run a time sharing system on one of our older machines, a 7044, which is a 36-bit machine. And so I'm really kind of depressed, thinking, God, I'm now being put in the back seat with an older machine. Of course, I had no idea that by taking that job, I would learn a lot about the operating system and of time sharing, which was new at the time. You'll remember that it got introduced on a PDP-1 from Digital Equipment Corporation. I think John McCarthy must have been
Yeah.
very much involved in that at MIT. and then brought that to Stanford University. So I had not really fully taken on board the value of staying at IBM, working on an older machine. Looking back on it, of course, it was very fortuitous. And also, if I hadn't done that, I wouldn't have met my wife. And we'll be celebrating our 60th anniversary next year.
60.
So,
That's
that's a
absolutely
very
amazing.
important decision that IBM made that had a massive impact on my future.
Yeah. And can you remember the memory size of these System 360s? I mean, they were measured in megabytes in those days, as I
They
remember.
were. I'm not sure that I can give you a good quote, but I think certainly a million words
Mm,
seemed reasonable.
mm, yeah,
They were 32-bit words, of course,
yeah,
not
yeah.
36 in some
Ah,
as in some of the
yeah,
previous machines. But
mm,
frankly, I would lose an exam on the 360. I would
yeah,
probably fail miserably, given that it's 60 plus years ago.
yeah. It just shows you how privileged we are now, having 1632 gigabytes of memory, and our programs are all very verbose.
It's
So,
pretty.
what's your memories of Steve Crocker, and what was his contribution to the creation of ARPANET?
So Steve is quite a remarkable and capable person, even at a young age. So when we were at UCLA in our graduate studies, um, Steve, who was born in 1944, and so we were at UCLA in 1966. So he would have been 22. Um, he took on the responsibility of organizing and managing something called the Network Working Group. This was a group of graduate students at something like a dozen universities, many of those universities doing research in artificial intelligence for the American Defense Advanced Research Projects Agency. The Network Measurement Center, where I was principal programmer, was set up to measure the performance of the ARPANET, a predecessor to the internet, a packet switch system for interconnecting computers together. And so in those years, we had many different kinds of computers from many different manufacturers, and they were all different operating systems, sometimes different character codings, certainly different word sizes. And they were not necessarily in any way compatible. So sticking them onto a network required some effort to make them all interwork properly. A company called Bolt, Beranek, and Newman made the packet switches of the ARPANET, and they were all uniform. But then you had to build an interface between the packet switch and whatever host computer it was. So Steve took on the task of organizing people to develop first the software that allowed each host to communicate. We called it the host to host protocol. It was the predecessor to the TCP IP protocols of the internet. So Steve led that effort. I participated in that development along with others. But he also was responsible for organizing the development of applications to go on the ARPANET. And so there were different groups in different universities or mixes of universities working on things like file transfer. Electronic mail, for example, got invented by a guy at Bolt, Beranek, and Newman who figured out that you could transfer messages from one computer to another as a file. You could transfer files. And so he's trying to figure out, if I send a file from one computer to another using this file transfer protocol, how do I tell the receiving computer which directory to put the file in? So, well, he said he had to know what the user was that the file was intended for. Then he realized in order to identify this information, he had to have a way of separating the user identifier from the host identifier. And he's looking for a character to separate the two. And the only one that he can find that isn't already in use for an escape character or something was the @ sign. And it made perfectly good sense, user at host. So Steve is responsible for uh, not only organizing all this, but he also sets up the request for comments that you mentioned earlier. And so his first request for comments RFC number 1 was issued something like April 7th, 1969, a very humble document saying, I think we should try to document what we're doing. We're not in charge or anything. And so that's why he called it request for comments. And the early exchanges were kind of like letters in the 18th and 19th century. I mean, people were these were not formal documents. These were exchanges that might well have been done by email, but we wanted them to be more formalized so there'd be a record. So Steve gets credit for recognizing that a record of what we were doing might turn out to be important. And today, looking back on this 60 years later, he's absolutely right. And there are lots of people digging in, the history of networking using a lot of the RFCs and some of the email that was involved. So he went on to join ARPA. And when he got there, he was running the artificial intelligence program, which is something that he had picked up while he was at MIT before he came to UCLA. And so he did that for 3 years at least, I think, and then returned to UCLA to finish his PhD. And without trying to reprise his entire history, he and I have worked together, and sometimes at the same time in the same place, and sometimes in different places, for literally 60 years now.
Yeah, that's amazing. I suppose the only problem with the email address is that it was round the wrong way. So you ended up with the domain at the end where it should have really been at the start. Because I think X500 defined the structure where com was at the top. And then, well,
Yes.
it wasn't
Yeah.
even com, it was US and UK and so on
Yeah.
and in what time. But we ended up the other way around, but it still seems quite natural.
Well, I remember X500 and X400. And I remember that in the UK in particular, they did it the opposite way. And so we had to build gateways that flip things around. Uh, yeah,
Novell, NDS architecture had it the other way around. And I think some email systems still have that top level OU country,
yes. Well,
OU.
the U.S. Defense Department adopted X400 for a while, bless their
Mhm.
hearts. I think they've long since abandoned it. But there was a big problem that showed up at one point because of the reversal. And there was a situation where one of the emails in reverse, in what I would call a reverse order, started out with cs.ucl. So on. And when that got reversed, the .cs came at the end. And that was a problem
It's
because
like
when the
different
domain name
country.
showed up, that was Czechoslovakia.
Yeah.
And it's a big collision.
Yeah, yeah, that's a problem. But it worked, and that was the killer app for the internet that really, apart from TCP/IP, that was the app that fitted onto TCP/IP that really allowed us to scale in. And you have HTTP was the big one. So many people debate about what ARPANET was all about and why it was created. So some would say it was only for academia and military to share computing times, share information. Other people say it was a network to survive a nuclear attack on the US. What do you think it was?
First of all, you need to understand a little more history. In 1962, Paul Barron, a quintessential engineer at Rand Corporation, was charged with developing a network that would survive a nuclear attack. And so he wrote an 11-volume series called On Distributed Communication. And the one of the volumes was classified, but everything else was not. And so he had conceived this mesh network of radio transceivers on telephone poles that would transmit data, across the United States. And if any of the poles got knocked down or other things broke, as long as there was some path in this mesh, then messages could get from point A to point B. So he was positing packetized voice way back in the early 1960s, before this was really feasible. Uh, and so he adopted this idea. He didn't call it packet switching, he called it message blocks. But almost simultaneously, maybe a couple of years later, a man at the National Physical Laboratory, Donald W. Davies, came up with an idea which he did call packet switching, And he got enough funds to build one packet switch. So it was more like a local area network. So he was experimenting with that around 1965. And Len Kleinrock, whose name I mentioned earlier because I worked for him in the measurement lab, had done his dissertation in 1961 at MIT on the statistics of packet switching. It was basically stochastic flow and delay in message switching networks was roughly the title, which became a book actually. So he did his dissertation and then came to UCLA and joined the UCLA electrical engineering department, and eventually a portion of it became the computer science department. So the ARPANET was created primarily to interconnect the universities that were doing research in artificial intelligence. And the whole idea was that if they could be interconnected, they could share their results and their computing capacity. So ARPA said, we're going to fund everybody. So don't hide your results, to have a competitive edge. Share your software and your computing capability and your ideas so we can accelerate the pace of artificial intelligence. Now, that's 1962 speaking. And here we are, 63 years later. It's taken a very long time for the acceleration to get to where it is today. But the aspiration that ARPA had was to advance the state of the art back then by building a network and allowing people to share their results. That was cheaper than buying everybody a new computer every year. So this was all motivated by economics more than anything else.
Yeah. And obviously Cisco from Sun, the from uh, from the Stanford labs, they had the concept of the router, and we're all used to that concept now. But in the early days, they were called imps, as I remember.
Yes,
What
for
role?
interstate message
Yeah,
processing.
that's right. So, what role did they have in actually scaling the internet up?
They didn't. They were part of the ARPANET, but they never made it. Well, let's put it this way. The imps were the packet switches of the ARPANET, and they were an essential element because they were essentially uniform. And so you could build the networking functionality in a uniform base, and then the host computers would use that packet switch network to communicate back and forth using the host-to-host protocols and telnet and file transfer protocols and the like, eventually email and other things. So the imps were a very important demonstration that packet switching to support computer-to-computer communication would work. The imps, of course, were used in the early days of the development of TCP/IP, but they were completely unaware of the internet. They had absolutely no awareness of it at all. Internet packets were carried in the payload of the packets of the ARPANET. And so the host computers implemented the TCP/IP protocols, but then they took the packets that were generated and they put them inside of the payload of the IMPS packets.
Like
And
like
the IMPS
Ethernet
back and
almost.
forth. When it got to the host computer, you threw away the IMP packet and pulled the payload into the TCP protocol implementation. Eventually, we split IP and TCP apart so that IP could support not only TCP, but also the user datagram protocol. So the imps really were they were an essential part of ARPANET, but they were not aware of internet at all. The things that were aware of internet were the host computers and the gateways between the networks, because all of the various networks of the early internet were completely unaware of the existence of the internet. Each net thought it was the only net in the world. And so rather than trying to change every network, we said, we will hide the fact that each network is part of the internet, but we'll use the payloads of the packets of each of the networks to carry internet packets.
Yeah. Because one time we used to get broadcast storms across networks before the days of gateways and routers, and that doesn't scale very well.
No, well, we ran into that problem with the Ethernet at one point,
Yeah.
where it literally, the best story though for broadcast storms was the vacation application for email. If you were going on vacation, the idea would be that you would automatically respond to any incoming email saying, I'm on vacation. One day, two people went on vacation at the same time, and each of their email systems sent to the other a message saying, I'm on vacation. And each system sent a message back to the other one saying, I'm on vacation. And there was this, and so we had to train the system to remember that it had already sent an email to someone, and don't do that anymore.
Yeah. It takes me back to Lotus. I think it was called CC Mail, which was
Yes.
a bit of a nightmare. Just one person would reply back, and then you would have multiple replies back from that. So we talked about John Postel, dearly departed from this world. What was his contribution in creating the standards for the internet?
So John took on an extraordinary role very early on. First, when Steve left UCLA to go to ARPA, he handed over the RFC series management to John Postel. So John was the RFC editor. He also handed over to John the responsibility for capturing and recording what addresses each host computer had been assigned on the ARPANET. And of course, as the internet emerges, the internet addresses have to be assigned, and John took that responsibility as well.
Wow.
And when the domain name system was created around 1984, he took on the responsibility for keeping track of the domain name assignments. So he was the RFC editor and the IP address manager, and also the domain name system manager for some years. With support from the Defense Advanced Research Projects Agency and the National Science Foundation, and some colleagues, especially at USC Information Sciences Institute. So, but he was not just a functionary. He was a bona fide researcher with a PhD in computer science. And he had a lot to say about not only the protocol design, but also how well it was documented. And no RFC would go out until John was satisfied that it was well enough written that it deserved to be in the RFC series. So John did that work for all practical purposes from 1969 until 1998 when he passed away, at which point other colleagues who had been working with him continued to support the RFC series, which goes on to this day. There are on the order of 10,000 RFCs now. In the long course of that history, and of course hundreds of protocols and enormous amounts of address space and large numbers of domain names, hundreds of millions of them. So eventually that had to be, could not be managed by even a small group of people. Now it's managed by large enterprises.
Yeah.
I,
Obviously, yeah.
I'm sorry to interrupt you, but you were asking about my recollections of John. One of the things that made John so unique is that he was, first of all, absolutely dedicated, and second, he was extremely well trusted by everyone. His judgment about matters was always, thoughtful and nonpartisan. He just cared about quality. It didn't matter who you were or what you thought. John would only accept things that were reasonable. And when people were in dispute and they would come to John to make a decision, he sent them away saying, you go sort this out and let me know what the answer is. So he forced people to come to grips with their disputes. So he was absolutely, I think, the most trusted guy in the internet universe.
Yeah. And some would say the editor of the if you co-created the internet, he was the editor of the internet. And RFCs broke away from the large companies defining the standards, such as IBM at the time,
Yeah.
and RFCs broke that up, and they were just so informal. And the ISO, CCITT standards, and all these other
Yeah.
bodies just melted away because they just took so long to be able to create
Well,
anything.
Well, they didn't melt away. CCITT is now the ITU.
Yeah.
The International Standards Organization still exists.
Mhm.
The Internet Engineering Task Force and the Internet Architecture Board still exist, and they still produce standards. Interestingly enough, the Internet Architecture Board was created originally by me because Bob Kahn said, "What happens if you get hit by a bus?" At this point, it's 1976. I joined DARPA. Maybe we'll get to that later. He said, "What if you get hit by a bus?" And they said, "Okay, we'll create the Internet Configuration Control Board, the ICCB," which I wanted to make sound so boring that no one would want to be on it. And then I appointed the people who were leading the research that led to the development of the internet to be on that board. And eventually that was turned into the Internet Architecture Board by one of my successors at ARPA. Anyway, let's keep going with the list that you've already created.
Yeah, and it's amazing when you think that John kept track of all those things such as DNS and IPv4, and they're still there. So we thought IPv4 would be migrated away to IPv6, but it's still IPv4 that runs the world, and it's still DNS that we're using. It's flawed, but it works really well. So it's really amazing that a human created this vast infrastructure of registration that's obviously been taken over by ICANN, much more, and it's fairly independent. No government runs it at all, and
Well,
it just
that took some
works.
real doing because ICANN was created in response to a request from the U.S. government, specifically the National Telecommunications and Information Agency, in 1998. So there were several responses, and the one that succeeded was the proposal from the Internet Corporation for assigned names and numbers. But it was responsible under contract to NTIA for many years until 2016. So literally on October 1st, just 2 days ago, 2025, that's the ninth anniversary of the separation of the Internet Corporation for Assigned Names and Numbers from the official government contract. So it took quite a long time from 1998 to 2016 before that separation actually happened.
Yeah, and I think you've you've changed quite a few of your jobs and moved companies. In 1982, I think you left DARPA to join MCI Communications Corporation. Why did you make that move?
Well, I left ARPA very late in 1982. And the reason that I decided to do that is that I had been doing the math on what my two sons' college educations were likely to cost. And I looked at my government income and I said, I probably won't be able to afford this on a government salary. And so I decided that maybe it was time to go into the private sector. And by happenstance, the year before, in 1981, I had been invited to meet the founder of MCI Communications and his vice chairman, and they wanted to figure out if they needed a chief scientist. So we had dinner together, and at the end of the evening, they concluded they didn't need a chief scientist because all they had to do was to say, "Here's a check for $250 million. I will buy $250 million worth of this product if you can build it." And they figured that the people who wanted the money would go do all the R&D and everything else. So I was still at ARPA after that dinner meeting. And then it was Bill McGowan and, oh dear, who who are the two guys that did the first flight in 1903? The flight of the first heavier than air aircraft. Who are the two brothers, the bicycle guys? Guy, why am I drawing a blank on this? Anyway, I had,
Right,
sorry?
right, right, brothers.
The
No,
Wright brothers. Yes,
yeah,
the Wright
yeah.
brothers. And so it turned out that Orville Wright was not one of the Wright brothers, but he was named Orville Wright, and he was the vice chairman or
Mm.
president of MCI. So it was with McGowan and Orville that I had dinner. Anyway, the following year, I got a call from MCI again from a guy named Bob Harcharik. And he said, listen, they want me to build a digital post office here. Can you come and help me? And that was basically an email service. And well, I've been using email for a decade because it had been invented by Ray Tomlinson at Bolt, Beranek and Newman in 1971, and we'd all been using it. So I said, sure, I can do that. So I was brought into MCI in 1982, late 82, to build MCI Mail, which I did. And so I had two reasons. First, it was an interesting problem. Second, I knew how to do it. And third, it was a better salary than the government. So I stayed there until 1986, at which point the basic development had been done. The system is in operation. There's not too much evolution going on. And Bob Kahn calls me up and says, hi, I've left ARPA after 13 years. I've started a new organization called the Corporation for National Research Initiatives. Would you please come and be my vice president? Well, the opportunity to work with Bob Kahn again was very attractive. And so I joined his company in 1986. And we spent 8 years together exploring applications of the internet. I guess I've gotten a little far ahead of some of the questions you've got. So maybe
No, no,
pause.
no, that's great. So I think you were the first creator of email with the work that you did there. So
Wait.
yeah,
No, let's set the record straight here. I'm not the inventor of email. That really, the title goes to Ray Tomlinson. However, the MCI Mail is one of an early commercial email service, not the
yeah,
first, but it
yeah.
was commercial. But it is the first commercial system to have been connected to the internet, because at the point where we do that, it's 1989. And in 1989, the commercial traffic was not allowed to flow on any of the government backbones of the internet of the day. So there's the original ARPANET, there's the NASA Science Internet, there's the National Science Foundation Network, and there is the Energy Sciences Network of the Department of Energy. They were all interconnected to form a huge backbone, internet backbone in the United States. But because they were federally funded, no commercial traffic was allowed on them. And I said in 1988, could I experimentally connect the MCI mail system to the internet just to see if we can get them to interwork? Of course, I designed both of them, so I had a pretty good idea of how to do that. And we succeeded in the summer of 1989 in getting MCI mail connected to the internet. And as soon as we announced that, all the other commercial email services, Telemail and On Time and so on, said, wait a minute, we want to be connected too. And they did. And then they discovered, holy cow, all of our customers, which we thought were, captured on a little island, can talk to all of our competitors' customers through the internet. And so suddenly the motivation for going to any one or the other of the email systems was diminished, because no matter which one you were on, as long as you were connected to the internet, you could get to all of them.
That's an amazing concept. I remember using AOL, and at one time everybody had to have an AOL address, and it was
Yeah,
quite strange if you were using a CompuServe or other address. There was no Microsoft or Gmail. In those days, you were locked in through your internet service provider to that email system. So,
so there's
yeah,
an interesting other little factoid here. When we launched MCI Mail on September 27, 1983, we had done a deal with CompuServe. So
mm,
all 90,000 CompuServe users were automatically given MCI Mail accounts.
ah,
And
all
so
right,
we had a direct interconnection between CompuServe and MCI Mail in 1983, late 1983.
yeah. And yeah, I mean, some of these companies just didn't move with the tide. I know that the circuit switched networks in the US just thought that packet switching would never take off,
That's
and
exactly.
AT&T AT&T were a massive company at the time, and they didn't even want to adopt packet switching because they had invested so much, and they just didn't think it was good. But the small companies, was it BBN? BBN was one of the first companies to really deploy that packet switch network.
That's right.
So we've ended up with a 32-bit address field for IP addresses, and we obviously have these classifications for the subnets A to E. Why was 32 bits? I mean, it just seems so small now. Why was 32
Wait a minute.
bits
Wait a
selected?
minute. Let's remember, this is a decision that's getting made in 1974. And first of all, this is an experiment, right?
Mm.
Who knows? How many networks were there at the time? Well, let's see. There was the ARPANET, there was the Packet Radio Network, and there was the Packet Satellite Network. 3 networks. Now, and how these are big, expensive networks, especially ARPANET. Okay. And down the street in 1973, Bob Metcalfe is building Ethernet. Okay, so that's a 4th packet switch technology, but it's a local area network. And who the hell knew how many of those there were going to be? So I'm thinking we don't really need a lot of networks, a lot more networks to test this idea, maybe a dozen or something. So we said, let's just take 8 bits for a network address. That's up to 256 networks. And we were thinking national scale networks, not local area networks. And we were asking ourselves at the time, this Bob and I are asking ourselves, well, how many countries are there in the world? And we guessed at 128. We were wrong. It was actually more like 175, but we didn't know that. And there wasn't any Google to ask at the time. So we said, okay, it's about 128, and maybe there'll be 2 networks per country, so there'll be some competition. So 2 times 128 is 256. That's 8 bits. Then we said, okay, so how many computers might there be per network? And we thought, well, 32-bit boundaries are normal for a lot of computers of that time. And so we said, well, why don't we just allow the remaining 24 bits to be the identifier for the host? That's up to 16 million computers. Now, remember, at the time this decision is made, computers were big, expensive things in air-conditioned units, which you described earlier. So we didn't think there were going to really be 16 million of them. So we just allocated the 32 bits. Now, what happens is very quickly is that local area networks start to proliferate. By 1982 or 1983, Bob Metcalfe has started 3Com. He's pumping out Ethernets like crazy. Universities are building local area networks. They're buying Sun Microsystems hardware. They're getting workstations. Haven't got to the laptop stage yet. So networks are proliferating, and at some point we realized that we're running out of network numbers, and so we reinterpret the meaning of the first few bits of the IP address, and we create Class A, B, C, and D networks. Class A networks had 16 million computers in them. Class B networks had only 2 to the 16th hosts computers, which is whatever, 65,000. So the whole point here is that we tried to reinterpret what the bits meant, and even that wasn't good enough because the Class B address space was being rapidly consumed by local area networks. So we went to what's called classless interdomain routing, which allowed the bits to be the network identifying bits to be bitwise identified, all the way down to the point where you have one network with only 256 computers on it, which is not an unreasonable small local area network. So the evolution of interpretation of the 32-bit address space reflected the demand for network identification. But even that wasn't enough. And so in 1992, we all recognized that no matter how we interpret the 32 bits, it's not going to be enough. And so there's an effort to invent a new IP format that would have a much larger address space. And we were oscillating between 64 bits and 128 bits or variable length. We abandoned the variable length because of the amount of computation that would be required to figure out where the other fields of the packets are. And so we eventually settle on 128 bits. 2 to the 128th is 3.4 times 10 to the 38th addresses. And I figured, okay, that's enough to last until after I'm dead. Then it's somebody else's problem. Now, you mentioned earlier that IPv4 is still a dominant component. Actually, it's not so clear anymore. Maybe about a third, maybe even as much as 40% of the internet is now capable of running IPv6.
Yeah.
The important thing to note, however, is that the traffic on the network is mostly IPv6 traffic, because a lot of it is video, and a lot of it is on mobiles. Now, there are billions of mobiles in the world, and many of them are smartphones with the ability to connect to the internet, and they're using IPv6. So a bulk of the traffic that's being carried in the internet today is source and synced at IPv6 locations, although not much more than 2/3 of all of the serving systems are capable of running IPv6. It will get there eventually. I am confident. It's just taking a lot longer than I expected.
Yeah, and the packet size has limited us. Like typically we're looking at 1,500 bytes for a
Yeah,
packet size, and now that just seems too small. But I think that's been eased up. I think some of the new TCP specifications are
yeah,
going for bigger
yeah.
packets.
We
So
we yes, we identified an alternative interpretation of packet length in
yeah,
TCP. That's correct.
yeah. I think with the Google Quick protocol now, it's much more dynamic, much more UDP, much
Yeah, that's
more
correct. That's correct.
connection orientated, that you can get a connection back. Where TCP/IP was a connectionless, well, HTTP, you connect and then you disconnect, you got to reconnect again. So I think there's obviously been a change. So you designed the IP packet. Let's call it packet. So I like to get these things. We would call it a data frame at Ethernet. We call it an IP packet. And this is where a lot of people go wrong. It's a TCP segment, not a
Yeah,
TCP
that's right.
packet
That's right.
overall. So you define those. Are there any fields that you regret? Because there's some fields that aren't really being used anymore, but are being used for other purposes. Are there any fields in IP and TCP that you regret adding and ones that you wish you had added?
Well, for a long time, at the very beginning, Bob Kahn and I thought that fragmentation was going to be an essential feature
That's
because
right. Yeah.
we didn't know how big or little the various networks would be, what their carrying capacity would be. And we were afraid that some TCP segments would be too big to carry in a packet for a particular network. And so we very carefully designed a fragmentation strategy so that you could take an incoming internet packet whose payload had a TCP segment in it and break it up into 2 or more packets in such a way that they could be reassembled at the other end. And we thought that was going to be a necessary thing. Well, it turns out that reassembly is a big problem, especially if the packets take different paths and they get broken in different ways. The guy on the receiving end is getting various and sundry different pieces of the TCP segment and has to sort of figure out how to piece the parts together. There was an RFC that said fragmentation considered dangerous or something like that. And so the solution to the problem is to try to figure out what the maximum carrying capacity is of the path that the packets are on. Now, this conflicts a little bit with the idea that the packet should be able to go any way that it can. And but it turns out that because of the way the routing systems work, it's especially the inter-network routing, the so-called border gateway protocol, the paths tend to get not set up, but they tend to be taken and be persistent. So the routing protocol doesn't, flap back and forth unless there's something wrong. And so the path detection, maximum transmission units, MTU detection, works relatively well because the paths don't change very much. So that's just a solution to the problem. So the fragmentation fields just weren't necessary. There was a type of service field that got created we didn't know exactly what to do with it, but the military said they needed to have a way of saying what was more urgent, what was less urgent, what needed to be delivered reliably, what needed to be delivered quickly, but not necessarily reliably. And so we put a TOS field in there, but I don't think it got used very much because it wasn't clear what would happen to a packet that went from one network to another. How is the TOS field going to be interpreted in the new network?
Mm.
What if you said, this is a high priority packet, and so you should carry it as fast as possible? It wasn't quite clear what the business model was on the next network. And so none of those things really worked out very well. And then it made what made things even more complicated was multicast, which also did not get widely implemented, but we thought was going to be important. Then the problem we ran into there was, suppose you had a single packet that crosses the border into a new network and it's going to multiple destinations. So suddenly the packet demand increases instantly as the packet crosses the border. And now the problem is the other guy is saying, wait a minute, you're asking me to carry 350 copies of this packet to different destinations, and you only had to carry one. So you should compensate me for that. Well, nobody wanted to do the old trick that the telcos used to do, which is negotiate charges, termination charges, and whatever they called it. There was a term for that. Anyway, we didn't want to do that. We wanted each of the networks to be able to run independently. So that turned, the multicast didn't work out very well either. So there were a number of things that we tried out or we thought were important, which turned out not to be. And so those fields didn't get used.
Yeah. I think some companies like Cisco did interpret the quality service fields where you can actually define low latency packets, because obviously you're now, it's not just computer traffic. Computer traffic is error free, doesn't matter how long it takes as long as it gets there, and you can check that if there's any errors. But then voice and video came along, which I don't care if it's got errors in it that much, but I matter how quickly it gets to there. So I think your protocols were designed in such a way that there was spaces for these things to be
Well,
created.
let me put some nuance here, because that tends to work okay within a single network,
Mm.
especially if
Yeah,
it's running all similar equipment like all Cisco or what have you.
yeah,
The problem here is that when you cross into another network, it isn't clear whether they will interpret those fields in the
yeah,
same way. So you
yeah,
could offer, a single network could offer these kinds of services, but it isn't clear that it would work across the global internet.
yeah,
Now,
yeah.
also, I should say that part of the way in which this question of capacity and latency was dealt with is by increasing the total capacity of the network to run faster and faster. Today, the backbone networks are running at 400 gigabits a second, soon to be 800 gigabits a second,
Wow.
and perhaps before the end of the decade, 1.6 gigabits per channel, per
Wow.
optical channel. And of course, in a single fiber, there can be multiple channels. So a lot of the latency issues went away because the only thing that was left was speed of light. And there's
Yeah.
nothing we can do about that thanks to Dr.
Mm.
Einstein. So we just kept increasing capacity in order to deal with latency for a long time. It's still true and as you say, that some networks were able to offer more well-defined low latency off services, but within the single network.
Yeah, yeah, that's true. And just yesterday, I was doing a lab with students, and I highlighted the importance of a default gateway. Your computer is not going to get out of the network. You need to
Yes,
discover what the router port is that you're communicating with, because it just doesn't. The packets don't just jump over themselves. So, could you
yeah,
outline the importance of gateways in the design of the internet?
it's fundamental. I mean, this wouldn't work without it. That is the fundamental design decision. When Bob and I started working on this, as I mentioned before, we had these three networks: the ARPANET, the Packet Radio Net, and the Packet Satellite Net, and they were all very different addressing structures, different networking technologies. And we said we are not going to retrofit internet into each of them. So each of those networks was completely unaware of the internet, and we kept it that way. So we said, well, there has to be something in between the networks that knows about the internet so that it can take the payloads of packets coming from one network, pull the internet packet out of the payload, look at it to figure out where it's supposed to go, and then put it into another payload of the next network's packet format and send it on its way. So this gateway has to look like a host to each of the networks it's connected to. And it has to know about IP because that's the only way we can know where things are going to go. What network is this thing going to and what host on that network? So the gateways were a fundamental piece of the architecture. And I remember drawing a sketch with a box labeled G, which said, this is the thing that pulls the packets out of the payload and puts them into the new payload and sends them on. And we wanted them to be state free. So we did not want to have to be forced to stick with a particular gateway to carry traffic. Because if the gateway went down and it had to be brought up again, what happens to all the state information that was in it? So we decided to make it as stateless as possible.
Yeah, that's really interesting. I spoke to Whitfield Diffie and Marty Hellman and asked them why they didn't patent their method, because if you think about it, every single connection that we make to the internet is using the Diffie-Hellman method. Rivest, Shamir, and Edelman patented their method and created a very successful company. MIT were obviously much more aggressive when it came to following up the patent and intellectual property than Stanford was. Why didn't you patent IP, TCP, and gateways?
Well, 2 points here. First of all, Stanford is fairly aggressive about patenting.
Yeah.
But this in particular, this was a Defense Department funded research. I don't think that was the case for the work that Marty Hellman and Whit Diffie were doing.
Yeah, some was military related, but you're right. I think it was like academic, independent research.
So they might have been in a position to do that, although I'm not clear either of them was thinking in business terms. In the case of the internet, however, Bob Kahn and I was still at Stanford at the time that we did the initial work and published that 1974 paper. But we both thought about this and wanted the design to be implementable by all of the American allies of the day. And because we said, if we're going to build this network for command and control, it has to interwork with the allied networks as well. Otherwise, why do it? And then we started thinking, we said, well, okay, so who are our allies? And then we had a list in 1974. And then we said, well, who were our allies 25 years before? And it was a very different list.
Uh,
And then we said, who will our allies be 25 years later? And we didn't have any idea. So we thought, okay, the only way we can be assured that the allies of the United States will be interoperable with our Defense Department command and control system is to make the protocols freely available. And we said, besides, there are competing things. You alluded to SNA at IBM. Digital had DECnet, for example, and HP had DS. And so we said, we want there to be no barriers for the adoption of this protocol. So we said, let's just release it freely without any restriction. Now, when you think about it, this is supposed to become the basis for the American command and control communication system. What the hell were we doing releasing this in the public? Of course, we had our motivation, which I've just described. But people ask me today, how did you get away with that? And I said, well, we just did it. Nobody noticed. So, and I would do it again because it's the only way to smooth the way of towards adoption. So that's why we did that. And I don't regret that at all.
no, I think he did a great job. I think it wouldn't have went anywhere. It would have been just a local commercial thing, and people wouldn't have adopted it. And obviously, you were up against the big companies like the IBMs and the DECs, who did want to lock down their systems, and you broke that. So it's a really great thing that you did. So
So
IP, yeah,
I'm sorry to interrupt you again, but two other thoughts occur to me. The first one is that when Tim Berners-Lee released the World Wide Web, he said he saw what we had done with TCP/IP, and he decided he wanted to do the same thing to make it widely available. Second, there was real competition, not only from the commercial sector, but also from the Open Systems Interconnection model, which was developed within the ISO, and of course X25 and X75 at CCITT, now ITU. So there were other contenders for standardized computer networking, and that too, I think, reinforced our desire to release this with as few limitations as possible,
yeah,
so as
mm,
few barriers for adoption as possible.
yeah. Yeah, you had the X25 packet switching, but Ethernet became the standard. I always remember the coaxial cables.
Yes.
And if you
Oh,
wanted to
yes.
connect, you'd have
The
to have a
great.
T piece. And
Yes.
if
That
someone,
big fat
yeah,
yellow cable. Yes.
that's right. And the vampire
Yes.
connections were,
Vampire
were,
tap.
were, were great. And if someone left the coaxial cable open, it was actually really bad because the signals bounced off the end and the whole
Yes.
thing started to slow down.
So here's a piece of irony for you. 2 weeks ago, I was in Heidelberg, Germany, at the Heidelberg
Mhm.
Laureate Forum, and Bob Metcalf was there.
Wow.
He got a Turing Award,
Yeah.
and all of us who have Turing Awards are invited to
Mm.
the Heidelberg Laureate Forum, along with the Fields Medal winners and other winners of major math and computer science prizes. So Bob is still going strong,
Wow.
and so is Bob Kahn. He's here in town with me in Northern Virginia.
So he created the GUI. I mean, he really created Apple, you could say, when Steve Jobs went to visit the park, Xerox Park. I
Yes,
think Bob showed him uh, the GUI, like a Windows GUI. He showed Ethernet and he showed the mouse.
yes.
And Steve Jobs thought the mouse was the most amazing thing that he'd ever saw.
Well, you do remember, though, that the mouse came out of SRI
Yeah,
International. It was
yeah,
Douglas Engelbart who
yeah.
built the
That's
online
true.
editing system,
Yeah,
and he needed a way for the user to point to a place on the screen. So they built the mouse to do that,
yeah.
and Xerox PARC adopted that with the Alto machine. So here's just because this is so amazing. Uh, After Heidelberg and Metcalf, I went to London and I had dinner with Alan Kay and his wife. Now, Alan
Wow.
is the guy
Yeah,
that invented the idea of a laptop computer.
yeah.
I forget what he called it now, but he showed us a mock-up in 1968
Mm,
of what it could look like. This is even before Xerox PARC. And the problem was he couldn't build it because the electronic parts were too big.
yeah.
And so he had to wait until, micro electronics got down to the point where you could actually build something that you and I would recognize as a laptop. So I saw Metcalf a couple of weeks ago and Alan Kay a week and a half ago. Um, and it's wonderful that these people who are giants in the field are still around and they're still contributing.
Mm. Yeah, I think it was Compaq who really destroyed IBM's business model. The IBM had such a monopoly. They created the PC. They went into a little company called Intel, and rather than building their own chips, and then it was Compaq who reversed engineered their BIOS, which was really their intellectual property, and then Compaq had the market for laptops. Quite an amazing story there.
That was amazing.
Yeah. So IP routing covers public routing and obviously routes between these gateways. But the biggest problem is the last mile, the last bit between the gateway and how does it discover? I've just switched my computer on. You either have a big registry for the whole internet that maps MAC addresses, that was never going to happen. But then the last mile is covered by a horrible little protocol called ARP. Could you explain how powerful ARP is, and why it's so useful?
Well, first of all, I think ARP probably arose because of the broadcast nature of Ethernet. And we all know that Ethernet has evolved dramatically over time. Metcalf says, it doesn't look anything like what I designed in 1973, but they still call it Ethernet because it's sort of a brand name. Uh, Anyway, the problem with is that in the Ethernet, because it was a broadcast medium, and you were supposed to just listen for the packets that were supposed to be for you, you couldn't know which host domain name was associated, or which IP address was associated with a MAC address until you said, hey, all of you guys out there, which one of you has this IP address? And please tell me what your Ethernet address is so that I can generate packets that will get your attention at the appropriate time. So ARP basically broadcasts a question, which of you is this IP address? And of course, from time to time, you ran into the problem that two guys would try to pick the same IP address and there'd be a collision and you get an error message. But ARP has been very important, especially in broadcast media. And it's been retained, even though it probably is not quite as necessary anymore because Ethernets don't broadcast anymore. They're much more, I would say, managed than they used to be.
Switched, yeah.
Yes, they're switched.
Yeah. And with RFCs, we moved away from corporate standards, as you say, the OSI standards body, the IEEE, and things like that. But obviously, you were up against commercial companies who were trying to set standards. So if someone bought an IBM, you would have to buy everything from IBM overall. Did you see any resistance from commercial companies with the rise of the RFCs?
Oh, enormous resistance, not to the RFCs. I don't think the corporate management wasn't even aware of what an RFC was. But there was enormous resistance to these common protocols as opposed to commercially controlled ones. There's a story which might be apocryphal, but it's a good story anyway, that Ken Olson, the then chairman of Digital Equipment Corporation, had a board meeting in which he said, how do we kill this TCP/IP stuff? So first, I've already mentioned that there was a lot of rivalry among the various major networking alternatives, OSI being one, X25, X75 is another, and TCP/IP.
IPX, SPX, Nobel.
Yeah. Oh, yes, all of that, which came out of Xerox. The Xerox network system was adopted in part by the word Novell. By Nobel.
Yeah, Nobel, that's right. Yeah.
System. So here's what I did. While I was still at ARPA running the program, I went to the laboratories of IBM, Digital Equipment Corporation, and Hewlett Packard. I didn't go to the to the commercial arm. I went to the laboratories. And they said, listen, yeah, we got this global internet thing. And you got a lot of computers. Would you like to participate in this? And of course, the lab guys said, yes, why would we not want to do that? So they all built versions of TCP IP in their systems in the lab. And at one point, I think Hewlett Packard had one of the largest, internets, corporate internets in the world, because they had locations scattered all over everywhere. So what would happen is that IBM would go to a customer, and they'd bring the sales guys, of course. And the sales guys would bring somebody technical, an engineer, just in case there were any technical questions. And they'd be pitching SNA and all the other IBM-based things. And some customers, this would have been where internet is starting to become visible because of the Interop show, which is a whole other story, in the mid-1980s, mid to late 1980s. So the customer would say, what about this TCP IP thing? And of course, the sales guys would kind of push back and say, well, you don't really want that. It's an academic thing and it isn't commercial standard. And then the engineer would say, oh, we have it running in the lab. And at this point, pulls the rug out from under the sales guy. So there was this ability to interconnect computers of different brands was very attractive for a lot of companies, because mergers and acquisitions often ended up bringing together computers from these two previously separate organizations into a common environment. And how the hell did they make all that interwork? And so internet was a good way to do that.
Yeah. I remember there was an 80-20 rule. So 80% of the traffic was local and 20% was from the internet. And what we thought was that it was going to be Novell, IPX, SPX. Every machine had an IPX address on it, and SPX was kind of like TCP IP. And then it just flipped. Unix networks were obviously different. They were much more internet based, and really they led the way because PCs were quite isolated. But it's strange to think that now virtually all traffic is internet bound and very little is actually local anymore. So it's quite amazing how it became into local area networks much more. So the ARPANET was using packet switching, while I think most other companies like AT&T and so on were still using circuit switching. I remember using modems that I had to use a dial-up, and I
Yeah,
remember the
yeah,
screeching of,
yeah,
what was it, 1400 bits per second,
yeah,
and then 2800 if I was lucky. So do you
yeah.
think there was resistance at the time for that move to circuit switching? Because you're destroying an empire. You're destroying these massive companies that have built up circuit switched TDM networks and invested so much. What did that feel like at the time?
Well, I remember I worked for a telephone company called MCI,
Uh,
and so we built optical fiber
yeah,
networks, and
yeah.
we served telephone traffic all over the world. But we also invested heavily in internet starting in 1994. MCI had gotten involved in internet way before that in 1986, 87, because it supplied the optical fiber network for the National Science Foundation network that was built in conjunction with IBM and with Merit, which is a Michigan experimental or educational research networking team. The three, IBM, MCI, and Merit, built the NSFNet backbone with support from the National Science Foundation. So the, the situation was that these big companies that otherwise would have run away from this whole notion of packet switching became invested in it. And so MCI, after having participated in the NSFNet backbone and later building what was called ANS, which was Advanced Network Services, in 1994, while I was still working with Bob Kahn at CNRI, they called and said, "Would you please come back and put us in the internet business?" And I agreed to do that. We built two backbone networks. One was called MCINet for commercial purposes, and one was called VBNS, the Very Broadband Network Service, which we built for experimental purposes at the request of the National Science Foundation. So the big telcos, at least the MCIs anyway, went down the internet path big time. And it didn't take very long, well, maybe we're talking a decade or so, before a lot of the telcos recognized that voice and data and video could be more flexibly and cheaply carried as internet traffic rather than dedicated circuits. And so I remember when British Telecom got rid of their circuit switches and bought packet switching equipment. And I went,
System X.
sorry?
System X, I
Yeah.
think it was called, as I remember.
Well, let's see.
Was it
System X might have been, I don't know if
after?
that was the BT, was that the BT design or
Yeah,
the
I
AT&T?
think I think
Okay.
it was
All right.
BT. Yeah.
Yeah, they were using the Swedish switches, if I remember right. Anyway, I asked the chairman of the board of BT why he did that, and he said because it's cheaper.
Mm.
It's just less expensive to run the packet switch systems, and it's more flexible. So today, I would guess that an awful lot of voice traffic is carried in packet form through the telco system. There are probably some little places where there's still step by, Strowger switches and other things, but they're in tiny little, remote places. Everything else is packet switched.
That's right. So we went from HP being the leader in TDM systems and circuit switching to Cisco almost overnight. It just took off
Yes.
massively. So you and Bob received the Turing Prize in 2004 for your joint work. and creating so many protocols, NCP, TCP, IP, and so on. So what made you such a great, what makes you such a great team?
Well, first of all, Bob was my senior by about 5 years or so. His birthday and my birthday are 6 months apart. His is on the 23rd of December, mine is on the 23rd of June. He was born in 38, and I was born in 43, so we're 5 years apart. So he was a mentor for me, and we had worked well together in 1970 when he came out to UCLA. I'm still a graduate student, and wanted to kick the tires of the ARPANET. This is when it had only 4 nodes. But he believed at the time that there were mistakes in the protocols that BBNN had implemented that would cause the system to lock up under certain conditions. And so I was the principal programmer for the Network Measurement Center, and I was able to program our Sigma 7 computer to generate traffic, artificial traffic, to inject it into the network and cause it to lock up, which is what Bob wanted to demonstrate. So we made it lock up in so many different ways. I almost wanted to get a little rubber stamp with a network symbol on it and stamp it on the side of the computer like the fighter pilots used to do when they would shoot down airplanes. So he goes back with a big smile on his face saying, look, folks, I've demonstrated that we have problems we need to solve. And so that collaboration went very well. Then a few years later, he goes to ARPA from Bolt, Beranek, and Newman. And that's when he shows up at my Stanford lab in the spring of 73 with this problem that he's got 3 different kinds of networks and he needs to figure out how to hook them together. And so we worked extremely well together. Bob is a big picture guy. He sees very far ahead, plans very far ahead, knows how to draw different parties together to make big things happen, like the Gigabit Network Program and the Digital Library Program at CNRI. And I'm kind of like the engineer who's down there trying to figure out how the hell they actually make this work. We early on in our relationship, I used to get very overheated because Bob would say something and I would listen and my reaction would be, this can't possibly be right. What the hell are you talking about? You must be out of your mind. And we very quickly discovered that when that happened, it was because we had different models in our head about what we were talking about. And of course it didn't make sense, because if the models don't match, your observations don't make any sense. So we very quickly understood that as soon as I started to get overheated, it was because we probably had different models. So we would stop and we would say, okay, so what model are you using? And we would agree on the model. Then we'd have our big argument, but at least we were agreeing on the common model to argue over. So it was an extremely productive relationship, and it has been for God, how many years now? 1986 to the present. So you can do the math. It's 14 plus 24 or something. Well, you go to 1970 if you really want to do the math. That's 30,
50.
54 years, 55 years that we've worked together on a variety of different things. And we still occasionally are able to get together and work on things. He only lives a couple of miles away from me here in Northern Virginia. So it's been a what I consider to be a very productive relationship.
Yeah. I think it just shows you the best teams are different people. And you need that abrasiveness to a certain extent to have some debate, but you do need to agree on things. So I think if you get the same type of person in a team, it really doesn't work for innovation. You need a big picture person, you need a detailed person, and you need an implementer, someone that takes you to market and so on. So what role did Al Gore have in the creation of the internet? Sorry to bring up
Well,
politics.
yeah, first, unfortunately, he's the butt of many jokes, which is very unfair. First of all, he had a very important role to play in the history of the internet. In 1986, he hosted a hearing that Bob Kahn attended, in which Bob introduced the notion of national information infrastructure. And at the end of that hearing, Al Gore asked the question, should we build an optical fiber network to interconnect the supercomputers that NSF and DOE were building to the 3,000 universities that are scattered around the United States to give them access to this computing power? And so several of us went off the following February to San Diego because the weather was better. And we came back with the National Research and Education Network program, which Al Gore supported as senator. And then later, of course, Al Gore becomes vice president. And in the early days of his presidency, he advocated for allowing commercial traffic to flow on the government backbones. So there was a Boucher, one of the House representatives, introduced an element of the National Defense Authorization Act, which is a must-pass piece of legislation every year. And the thing they introduced was the official permission to carry commercial traffic on government backbone networks, the four that I mentioned earlier in our conversation. So Al should get very significant credit for policy related to the success of the internet. Unfortunately, when he was running for vice president in 2000, someone asked him what he had done when he was senator. And he unfortunately worded it as, while I was senator, I took the initiative in creating the internet. He was thinking about his policy development for, for the National Research and Education Net, which led to the NSF net backbone and 13 intermediate level networks. But it was deliberately misinterpreted by the opposition as claiming to have created the internet or invented the internet. Al is a very good friend. We correspond regularly. We don't see each other terribly often, but he absolutely deserves credit. Bob Kahn and I wrote an editorial summarizing his role and his contributions, and I will never forgive them, but the editors of the New York Times, the Washington Post, and the LA Times refused to publish the op-ed. So if your listeners would like to go to the internet and Google Vint Cerf, Bob Kahn, and Al Gore, the chances are very good that that op-ed will pop up, and they should read it. If there's any doubt in their mind, Al deserves credit for his contributions on the policy side.
Yeah, excellent. Yeah, I mean, you need politicians there. Most politicians didn't even recognize the internet for 30, 40 years. It's only now that they realize it's got such an impact. So I know that you have hearing deficiencies and you've coped with it very well. It must have been really difficult in the early days of these meetings that you have to discuss the RFCs, to be able to cope in those meetings. So what kind of strategies did you use to overcome those problems?
Well, strategy number one is hearing aids. They really work. I mean, it makes a big difference. And I've been wearing them since I was 13. So that's the first point. The second one is that starting in 1971, email became available. And of course, I was among the first to use it while I was at UCLA doing my research there on the internet. So I've tended to work for companies where email was a popular way of communicating because that lent precision and I didn't have to keep asking people to repeat themselves. But mostly, I'm very open about the fact that I have a hearing problem. And so I tell people, this is, you need to get my attention before you start talking to me so I know that you're talking and maybe I can see you deliberate. And so whenever I have meetings, I try to make sure I have a quiet environment. There are some new technologies around that are dramatic. One of them is a product called Live Transcribe. It's a free application on any Android phone, which will provide a transcription of what the microphone is picking up in up to 200 different languages. And so my wife, who wears cochlear implants, and me, who wears hearing aids, use this a lot as a backup for communication. So, it wasn't a hard thing to cope with, especially if you're comfortable telling people that you might miss something. And people have been very cooperative, in recognizing that I might need a little help from time to time. So it has sensitized me, though, to the importance and value of assistive technologies, and also the importance of accommodation for people with various kinds of disabilities.
Yeah, yeah, excellent. I'd completely agree. And so most people would know you as a dapper dresser, and I think we can see today that you have your usual three-piece suit on. Why did you pick that? And I know that you don't pick, but why do you select that type of dress style when most in the industry, especially John and people like that, were
Yeah.
much more casual with their dress sense?
So this tendency starts in high school. I wasn't wearing three-piece suits in high school. That would be way over the top. But I tended to wear a sports coat, a tie, and slacks in high school. Why did I do that? I wanted to look different from everybody else in school. It's simply a way of standing out. It gets attention. And I carried a briefcase. I guarantee you nobody else would be caught dead with a briefcase. And when I wasn't wearing sports coat and tie, I was in a military uniform because I was in the reserve officer training program in high school. So then I go to Stanford, and I'm much more casually dressed there. And then I go to IBM. Well, IBM, it's a white tie, or white shirt. I mean, not colored shirts, white shirts and tie. And so I had a suit. I wore a suit to work, or a sports coat and slacks and a tie, because that was the IBM standard. Then I got to UCLA, and I'm a little more casual again. Then I get up to Stanford to join the faculty. And at this point, I'm Professor Cerf. And I figure, well, I should dress the part. And so I went back to a suit or a sports coat and tie and slacks and a briefcase. And so I'm at Stanford dressing a little bit more dressily than a lot of the other people do, certainly the students. And then I get a call from ARPA, and they say, why don't you come back and run the internet program? And I said, no. And they said, why? And I said, it snows back there. And they said, well, we want you to come anyway. So I talked this over with my wife, who's from Wichita, Kansas. And she says, well, we've never lived on the East Coast, so, maybe we should try that. And then she says, Washington, D.C., three-piece suits. So she goes to the Stanford Shopping Center, and she buys three-piece suits, one of which is a seersucker outfit, which is, lightweight material because it's hot and muggy during the summertime in Washington, and she knows that. So I show up at ARPA in my three-piece suit. Nobody seems to notice. I mean, other people are wearing suits and ties. So one day, early on in my time at ARPA, I get asked to testify before one of the congressional committees. So I show up in my three-piece seersucker outfit, and I give my testimony, go back to work. A few weeks later, I get a call. It's from the director of ARPA. He's, two levels up, and I'm sitting here. He says, I want to talk to you about your testimony. And I'm thinking, oh God, I've screwed up. It's the end of my government job. So I show up in his office, and he's got a piece of paper in his hand. And he says, I have a letter here from the chairman of the committee, and I'm just waiting, for the shoe to drop. And he said, well, the chairman said, thank you very much for Dr. Cerf's testimony. By the way, he's the best dressed guy from ARPA we've ever seen. And I took that as positive feedback, and I've been wearing three-piece suits ever since.
Good. Yeah, that's an excellent explanation. It helps your career. I'm sure writing amazing IEEE papers and RFCs did much more. But as you said, it makes you stand out, and people remember these things. So I think it's really important. And you worked as a VP, and you've worked as a VP and Chief Internet Evangelist with Google since 2005. What does that role involve?
So a lot of people say, what does the chief internet evangelist do? And I didn't actually ask for that title. When I joined Google in 2005, uh, actually, I had sent a note to Eric Schmidt asking, who was then the CEO of Google, who had been the
Yeah,
CEO of Nobel.
co-founder. Yeah,
Yes,
yeah.
and so I said, Eric, do you want any help? And he sent a note back saying yes. That was my job interview. And at that point, Larry and Sergey and Eric got on a call with me, and they said, "What title do you want?" And I said, "Archduke." And, and so they went away and they came back and they said, Archduke doesn't exactly fit in our, hierarchy. And besides, the previous Archduke was Ferdinand, and he was
That's right.
assassinated in 1914, and it
And
started
caused
World War One.
war. Yeah, that's right.
Maybe that's a bad title. Why don't you be our chief internet evangelist? And I said, okay, I could do that. So it's an interesting role. We're just making it up as we go along. I started out from some over a decade at Google in the research department.
Mm.
Then I moved into the policy group for a while. Then I moved over into the public sector sales group for a while, particularly interfacing with government activities in the Defense Department and other, the Department of Energy and NSF and the like. And then I moved into the networking department, which is where I am now, where we're rebuilding the entire backbone network to be more resilient. The role has had a policy component to it for most of the time I've been there. I've been given the freedom to interact with any part of Google that strikes my interest, and people have been very kind to allow me to do that. And there are some outside activities that Google has also allowed me to undertake, and I think you have some questions about that. So it's been a magical period in my career to be here at Google for literally 20 years now. And the opportunity to meet some of the smartest people I've ever dealt with and to participate in the creation of new products and services in one way or another has been just hugely rewarding. And of course, it hasn't hurt that the company has done very well too, from the economic point of view.
That's right. Yeah, I mean, they obviously have grown so much over 20 years. You must have seen them really change. Because I think of IBM as having some of the best people in cryptography, especially in the New York lab. Like the people who came out of that lab were mentored by some amazing people and just went into academia and they flew. So I think when industry R&D works well, it actually works better than academia. Academia doesn't have the impact, doesn't have the power. As you say, you moved because you needed a better salary. Academia couldn't give you that. So I think when it works, and IBM were an exemplar at one time, but I think Google have taken over that role in terms of research, like real core research work.
So actually, let's arm wrestle about this a little bit,
Yeah.
because my career has oscillated
Mm.
in different sectors. I mean, I've worked in the private industry at Rocketdyne, for example, and Atomics International, and Space and Information Systems Division of North American Aviation. I've worked at IBM. I was at MCI for 11 years, and have been at Google now for 20. But I've also been in academia. I was at UCLA doing my graduate work. I spent 4 years at Stanford on the faculty. I still teach from time to time. And I run a number of nonprofits. I was chairman of ICANN for many years. I've got 4 nonprofits that I'm currently either chairing or involved in that Google has allowed me to participate in. So the point I want to make here is that oscillating between academia and industry often is re-energizing. So, you're in industry for a while and you're trying to create products and get them out there. And then you want some time to just think and to, explore ideas that don't have the pressure of revenue generation and profit making. So for me, oscillating around all three, nonprofits and academia and the business sector, I've even held special government employee roles at 6 or 7 different agencies in the US government. I still am a special government employee for some of them, like the National Institutes of Standards and Technology. So it feels to me like I've had a very rounded career in the sense of interacting with all those sectors, often concurrently.
Yeah. I think you do see that. I talk to many world leaders and they've often got a foot in both camps. They still like teaching, actually, and interacting with students and supervising them. But that cutting edge really needs to happen. The impact happens in industry. So I think it's very healthy to have a foot in both camps. Sometimes academics will leave and go into industry and never come back again. But I think, as you say, many times you want to come back and contribute in different ways. So I think you've worked on the interplanetary internet with NASA. Can you outline how that works?
Yes, I'd be happy to. You may recall that in 1976, the Americans landed 2 Viking landers on Mars. And that was a spectacular event because getting something to land successfully and then send data back is not easy. So that was extremely exciting. We got a lot of very, very intriguing data back. There was some indication, which was controversial, about potential for life having been on the planet, but it was inconclusive. Then for 20 years, from 76 to 1997, nothing worked. We'd miss the planet, burn up in the atmosphere, smash into the planet because we got the units wrong. So in 1997, a U.S. Mission called the Pathfinder mission successfully landed a little rover called Sojourner on Mars. And I got so excited that we had succeeded finally after 20 years in getting back on the planet that I got together with the communications team at the Jet Propulsion Laboratory to find out more about how they were communicating with the rover and the lander. And we started completing each other's sentences in the first few minutes. We got all excited, and then we said, okay, so what should we be doing now, that is to say in 1998, that we're going to need 25 years later? And we concluded that we should be looking at a solar system-wide internet. And we thought, well, internet seems to work okay on Earth, so it would probably work okay on Mars. But then we started doing the math, and we realized that the distances between the planets are literally astronomical. And the result is that it takes so long to move from Earth to Mars. It's 3.5 minutes one way at the speed of light, 7 minutes round trip time. When we're closest together, which is about 35 million miles. When we're farthest apart, it's 235 million miles. It takes 20 minutes one way and 40 minutes round trip time. The TCP/IP is not going to work with that kind of latency. And then there's another problem. The planets are rotating and we don't know how to stop that. And so if there's something on the surface and the planet rotates, you can't talk to it until it comes back around again. So unless you have an orbiter, and even then the orbiter might, disappear behind the planet. So we said, okay, what we have is a variably disrupted and delayed environment. The connectivity between the planets or other spacecraft is variable depending on the orbital dynamics. So we said we better design a suite of protocols that will take into account those additional challenges. So we developed something we call the Bundle Protocol Suite. And it consists of an end-to-end protocol, which is the analog of IP, although it does much more than IP does. And then there are underlying protocols at the link layer, for example, the Licklider transfer protocol. So the Bundle Protocol Suite stores information in the network, unlike the internet. In the case of the internet, when a packet shows up and there's no place to send it, you throw it away because you assume the origin will retransmit. That's how QUIC works. That's how TCP works. But retransmitting something from Earth to recover from throwing packets away on Mars that are supposed to be on their way to Jupiter doesn't make any sense. So we store this information in the network, which creates a challenge for the bundle-based routers, because now they have to manage significant amounts of memory and with bundles on board, waiting for those bundles to be transmitted to the next hop. So the system is quite different. We added a lot of access control and cryptography, validation using digital signatures, and a lot of other mechanisms, including new network management techniques. It used to be that in the early days of internet, you use a command line interface to send commands to a router that you were responsible for.
Yeah.
Well, you can't do that interactively when it takes 40 minutes to get a signal back and forth, or worse. I mean, the Voyager spacecraft are now 15 billion miles away. It takes 24 hours for a signal to get there,
Wow.
and another 24 hours to come back. So you're not going to use command line interfaces. So we've developed a new management suite of protocols where you send blocks of commands to tell the destination management system how to configure itself to do things more automatically. So that protocol suite has been in implementation since 1998. Prototypes have been running on Mars since 2004. Since 2009, we've been running the latest protocols. We've been upgrading as we go along. We're now at Bundle Protocol version 7. So the International Space Station has been exercising the protocols largely between the space station and Earth. We've done laser communication tests with the protocols. We've done tests to the moon in orbit around the moon. We're on the Artemis mission. We'll be part of LunaNet, which is the American Lunar Network. And ESA, the European Space Agency, JAXA, the Japanese Space Agency, and CARI, the Korean Space Agency, are all collaborating on this solar system internet implementation. So this has come a very long ways since 1998, and we're in the process of operationally deploying the capability.
That's excellent. And I think President Barack Obama appointed you to lead the National Science Board from 2013 to 2018. Can you outline some of the key areas that you worked on?
Well, the National Science Board oversees NSF, and its job is particularly to review major program expenditures, and also to oversee the emphasis, the areas of emphasis, which in theory should follow the president's areas of primary interest for research. So I was involved in some of the major decisions at the National Science Board. Some of them had to do with increasing the talent pool, not only from the research point of view, but from the technology point of view. So technicians are vital to research because they're the ones that actually get things done, while the researchers are speculating on what can be done. And the interaction between, let's say, astrophysics and the technology that's needed to do measurements is really interesting, because maybe somebody has a theory and they want to test the theory by doing an experiment. And so they find the engineers and the technologists to go build the equipment to do the experiment. And the engineer comes back and says it doesn't work. And the researcher says, well, of course it should work. I mean, here's the theory. And when they finally figure out it's not working for legitimate reasons, suddenly the theory might be in question. And so there's this back and forth tension between the engineering side and the research side, which I find very, very productive. So the NSB doesn't necessarily initiate things, but it responds to requests for major expenditures and for direction of research. I was very involved in the National Ecological Observation Network that NSF sponsored, which was trying to gather climate and other environmental data so we could start doing a better job of building models for how the world's environmental ecosystem works. And so that was an interesting experience because a lot of issues arose with regard to data collection, standards for metrics and measurement, the absorption of and management of large databases, the integration of sources from many different places. So that was very much in line with my experience with the internet and the whole problem of making use of large quantities of data. It was a very rewarding time in my career.
Yeah, yeah, well done. Access to the internet is probably a human right these days. We're probably not far away from that happening. And do you think the internet has been a good thing or a bad thing? I know it's not black and white. It's impossible to say. Uh, is it a good thing or a bad thing? And what were the mistakes that we've made in actually building it?
Well, there are people who think that we could have done a better job of detailed design. One place which there's a question about whether this is a little detail in a way, but it's a significant one. If you have a host on the internet or a router and it's connected to multiple networks, one question is whether you identify the port that a wire is connected to, which is how the IP addresses are interpreted, or whether you identify the node and not the specific wire that things came in on. And I had, for a long time, thought I didn't know how to do the node identification without saying very explicitly, it's this port that you want to send the packet to. And so I'd always thought that the routing system had to identify the destination port on the computer. But in the case of the interplanetary system, we've done it a different way. We identify the node that the data is going to, and we use the routing tables to take care of getting it to that destination without having to be so explicit as to the ID of the port. So that we could argue one way or another, but the fact that the internet is working and serving people says that it couldn't have been a fatal mistake. I think the biggest challenge we have is not technical. It's the way in which the internet and the World Wide Web, which sits on top of it, is used or abused. And I don't think that we fully appreciated what happens when you offer a universal bulletin board for people to put anything they want to up on it so anyone else can see it. And of course, if you're thinking in terms of data sharing and research and the acceleration of research because of mutually shared data, that all looks like a good thing. But when you start looking at social media and you begin to see some ways in which the social media are potentially harmful, you realize that we have work to do to find ways of reducing the harmful side effects of this global megaphone while not losing all of the amazing advantages of sharing information in a free way.
Yeah, 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 I agree. And what's your feelings about the rise of Gen AI? Is it a good thing or a bad thing
Yeah.
for society?
Well, this is just the same argument that you can make for the internet in general. It's that powerful tools can be applied in harmful ways. So hammers can pound nails and they can pound heads, and it's not the hammer that makes the decision, it's the person. So a lot of the potential hazards of Gen AI might come from abusive use of this powerful technology. But I would also say that when you give software more autonomy than it deserves, you run risk. That's not just the case for Gen AI. It's true for all software.
Yeah.
I mean, whenever I get into one of those elevators where you select the floor you're supposed to go to, and it tells you go to elevator B. So you get in elevator B, and there are no controls, and you realize, holy crap, I'm now at the whims of someone else's software that I didn't write. So why should I trust it? And it makes me nervous all the way up to whatever floor it is I'm supposed to get off on. So we should be worried not just about Gen AI, but we should be worried about software in general and offering that software more autonomy than it is safe to offer. And I think we have a lot of work to do there to be concerned about safety and security and privacy and resilience and reliability, regardless of whether it's Gen AI or just any piece of software that we are asking to perform for our benefit.
I agree. Operating systems like Windows still crash. They've been
Yes.
around for 40 odd years and we still get a blue screen. So we're not actually that good in designing and implementing software. I think Gen AI needs to have a kill switch architecture just in case it decides to kill us as a society or do damage. So obviously we need to be thinking much more, as you say, about the software, what software can actually do, and especially how it becomes distributed and we lose the control. So what does the future of the internet hold and of networking? Where, if you were to look at a crystal ball, where are you looking into the future?
Well, we've already talked about the interplanetary internet. I can also tell you about the interspecies internet, which is a project that's been underway since 2013 with Peter Gabriel and several other colleagues.
Um,
We're looking at how non-human species communicate with each other. We're interested to know whether we can understand what that communication means and whether we could engage in direct interactions with non-human species. There's a lot of data being collected by the interspecies internet team from interactions with multiple species, observing how they interact with each other. We have lots of digitized whale song. We have people who are working with dolphins. We're working with elephants. These people who are part of this environment are working with a variety of different animals that have a significant cognitive capacity. Gray parrots are amazing, for example. So we're hoping eventually to crack the code, so to speak, where the artificial intelligence power of the internet might be used to literally interpret the signals that we're getting from these non-human species so that we could at least understand their own interactions and maybe even interact with them, or even imagining having, a whale interacting with an ape. Of course, I'm not quite sure what they would talk about because they'd have to have some common shared experience to understand each other. But the internet might sit in between using AI to do the transduction. So that's one thing. There's another project which I'm involved in, which has to do with the preservation of digital information. If you imagine yourself in the 22nd century looking back on the 21st and wondering what went on here, the only way you could understand it would be to have access to the electronic mail and the files and the web and all this other stuff. And yet there's no guarantee that any of that data is going to last for 100 years, let alone 1,000 or 2,000. So I'm very concerned about being able to preserve digital content in a way which is interpretable. And that probably means being able to run old operating systems in the year 2100 or 2200 and run old applications in order to interpret old data files. You have to understand what the data file formats are. And I'm sure that you and your students could easily imagine a variety of challenges and information you wish you could have 1,000 years from now so that you can understand the digital content of the time. So that particular project is called Digital Vellum because vellum is sheepskin and calfskin and lasts 1,000 years. The question is, can we make a digital version of vellum that will last 1,000 years? That's what that project is about.
yeah, that's just really interesting. And my penultimate question, thank you so much for answering so many of my questions and using up all your time. If you hadn't been the co-creator of the internet and a networking evangelist and all the other things that you've managed to do, you dropped in that you worked with Peter Gabriel. Peter Gabriel, well, that's the rock star, I assume. Yeah, that's quite a privilege to work with someone like that. What career would you have actually taken? Let's go back when you left school. If you hadn't taken the route that you were on, what would you be now?
Well, I might very well have gone down a microbiology path.
Yeah, I
And the
thought
reason
that.
I say that is that I have become very interested in
Mm,
the microchemistry of the cell. I've got this gigantic book called The Microchemistry of the Cell, which is written by Bruce Andrews and a number of other National Academy members. And I've become extremely interested in what we can know or what we do know about how life works. And we, of course, have learned a lot over the course of the last 60 years. Um, Looking back, if I had not gone down the path I did, I would rather have hoped I'd gone down a related path in the sciences. I knew when I was 10 years old that I would be a scientist of some kind. I just didn't know what kind. For a while, I thought it was going to be nuclear physics. I was fascinated by Scientific American articles on particle physics and the fact that we're all made up of little neutrons and protons and electrons. Until then, we discovered that they were made up of quarks, and who knows whether the quarks are unitary or whether there's more to it than that. I didn't Physics and I didn't get along as well as mathematics, and so I went down the math and then the computer science path, and I don't regret that. But I think microchemistry and microbiology would have been an alternative for me.
yeah, I can see that exactly. And my ultimate question is, any regrets in your career?
Uh, One particular one, and that is failing to join Google before it went IPO.
Of course.
But I missed it by 1 year.
Yeah.
Uh, but honestly, I certainly don't regret having come to Google, and I do not regret any of the other experiences in my career. Except there is another one now that I think about it. MCI was acquired by a company called WorldCom in 1998,
Mm,
and WorldCom went bankrupt in 2002, and that was very costly
mm,
personally for me. And so I have to admit I regret that too. But I survived, and life is good, so it wasn't fatal.
that's amazing. So thank you so much. I mean, you've contributed so much to our world, probably more than virtually any person on the planet. That's just a personal opinion, but I'm sure a lot of people will back that up. I see you've got some photographs and some awards on your wall there. Can you identify maybe one or two of them?
I will do that, but I want to respond to your comment.
Mm,
You should not impute to me alone all of these accomplishments. They were done in teams with teamwork,
mm,
and literally, with regard to the internet, millions of people have
yeah,
contributed to it. All the people who build applications for mobiles, all the people that keep the internet running every day, because it doesn't run by itself. It breaks. People have to fix things. It has to evolve and expand. I mean, there are a huge number of people have made the internet and the World Wide Web what it is now, and we should remember to give them credit. That's why I tell people that lesson number one, if you want to do something big, get help, especially from people who are smarter than you are. I've been really good at that.
yeah.
So the pictures on the back wall, there are photographs of Queen Elizabeth giving me and several of my colleagues the Queen Elizabeth Prize for Engineering in 2013. That's a 1 million
Wow.
prize, which we shared.
Mm,
There are photographs of Al Gore. There are photographs of President Obama, photographs of George W. Bush giving me and Bob Kahn the Presidential Medal of Freedom. There are photographs of Bill Clinton giving us the National Medal of Technology. There are memberships in the National Academy of Engineering and the National Academy of Science. Uh, I'm sure there's a lot of, oh, there is also on the wall a big silicon disk signed by
mm.
Jack Kilby, the guy who invented the integrated circuit in 19.
Transistor and yeah, yeah.
Uh,
Wow.
I had gotten the Kilby Award a few years ago, and then Jack was nice enough to sign a silicon wafer for me, so that's on the wall as well. And of course, this is what I call the ego wall. And you can tell that I've carefully arranged my camera to pick up the ego wall and not the rest of my messy office here, which is in the basement.
Yeah.
Uh, so this is a snapshot of many other things that I don't have wall space to put up. So I have map drawers full of certificates, and it actually is now 33 honorary degrees.
Yeah,
Um,
33. That's
for, for,
amazing.
and interestingly enough, some of the colleges have given me their academic regalia,
Wow.
and some of it's extremely colorful,
Mm.
especially in Spain.
Yeah. All right.
And when I was at Stanford on the faculty marching in procession during the graduation ceremonies, I was wearing this kind of plain black thing with a black mortarboard. The guy in front of me had a degree in mathematics from the University of Madrid, and it was this
Uh-huh.
brilliant red outfit with a great floppy hat. And I had academic regalia envy for years.
Yeah.
Now I've got a dozen academic regalia. And so yesterday, celebrating my 20th anniversary at Google, I donned an academic regalia from the University of the Balearic Islands. And because I had worn that on my first day at Google, because it was the most ecclesiastical outfit I owned. And I wanted people to know that I took the role of chief internet evangelist seriously, and I still do.
Yeah, that could be your Archduke uh, costume if you wanted. Well, it's been a real pleasure, and you're right. I mean, in research, everybody contributes that little bit, and they share their ideas and don't lock them down. Your co-invention of IP and TCP really unlocked a key that took us forward, that broke the monopoly of commercial companies from the past. So I think you can't underplay that magic that just happened, and then you've continued to really contribute to so many other things. So thank you. That's been a really enjoyable couple of hours that we've spent, and really have a great rest of your day. And hopefully we'll see you sometime soon in the UK. Thank you.
I would look forward to that, especially if I had an opportunity to get to Scotland. Uh,
That
so,
would,
Bill, thank you again. Just remind your listeners that Bob Kahn was an integral part of this whole
yeah,
thing, and without him, nothing would have happened because he started the project and asked me to join him, not the other way around.
yeah, yeah. I totally agree. And the way that you worked together was first class, and it's been a wonderful development of the internet. I've seen it from AOL and dial-up modems and things like that, and just every single year we advanced, and we've now built this super highway that we now need to use properly. This has really just been a training period. Now it's serious. So thank you so much, and enjoy the rest of your day. Thank you.
Thanks so much, Bill. See you on the net.
Thank you.